Okay, we're going to continue on here to chapter 12. So we're going to talk about bonding in this chapter, and we're going to talk about obviously the two types of bonding, and those two types of bonding is an ionic bond and really a covalent bond. And as we'll talk about in this chapter, really the major difference between them is in an ionic bond, there's no sharing of electrons. Things are held together by opposites attract, so a positive ion and a negative ion is what holds that together. And the main difference there with the covalent bond is there is some type of sharing of electrons that are happening. And as we'll talk about here, it can be equal sharing of those electrons or unequal sharing of those electrons. But there is some type of sharing that's happening between the two. And that, again, is the major sort of difference between these two guys, and also what's involved is also different in terms of what elements are involved in an ionic bond versus a covalent bond. So let us get into some of this here then. All right, so one of the ways that we do represent bonding, both ionic bonding and covalent bonding, is we use Lewis dot symbols. They're sometimes just generically called electron dot symbols. And when bonds are formed, as we've talked about, I think it is only really the outer regions that come in contact with each other, and those really are the electrons. And there's really kind of the special type of electrons that are involved in bonding, and those are the valence electrons. And the valence electrons are the outermost electrons. They're the highest in energy level. And that makes sense if you think about sort of electrons on the outside. So when atoms sort of come together, the electrons are involved in a normal reaction. We talked about there is that conservation of the elements, and that means in a normal chemical reaction, it's just the electrons that are involved. We don't do anything with the nucleus and the protons. And as we talked about, I think in the previous chapter, protons are the most important thing in terms of what element you're dealing with. So as long as the protons stay the same, the elements stay the same. So really here it's just the electrons making and breaking bonds. So when we look at something like, say, magnesium, for example, it has 12 electrons. And if we write what's known as electron configuration, which is chapter 11, and they moved further back in the semester, so we don't talk about it yet, but we will eventually. We got something like 1s2, 2s2, and 3s2. This is the electron configuration. These first numbers here represent the principal quantum number, which is a fancy way of saying energy level. So those are abbreviated with an N. So if N equals 1, that is the ground state. That is the lowest in energy and closest to the nucleus. They can go to values of like N equals 1 through 7. So like 2 through 7 are higher states of energy. The S's, the P's, the D's, and eventually the F's, these are orbitals, and these are in an atom where electrons are basically found. And really for our purposes in this chapter, the number up on top as well. These numbers up on top are the number of electrons in those orbitals. So if we look and just count up those top numbers, we got 12 going on, which is how many electrons magnesium has. And if we just look at the front numbers, the highest energy, our biggest number that we see there is 3. And that means that magnesium here would have 2 valence electrons. And those would be the valence electrons. The lower energy level electrons, they're sometimes referred to as core electrons. Core electrons are closer to the nucleus, which means that they feel like the full brunt of the positive charge in that nucleus, and that means that they're pretty much held pretty tightly and they're not going anywhere. So it's only those outermost valence electrons which are flying around, not as close to the nucleus, not really being held as tightly, that are able to sort of participate in bonding, and those are the valence electrons. So one way that you could sort of figure out the valence electrons is to write the electron configuration. But since this semester we leapfrogged 11 to go to 12, probably the easier way, even if we did a chapter 11 to figure out valence electrons, is it will equal the group number. So 1, 2, skipping transition metals, 3, 4, 5, 6, 7, and 8. So everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, and 8. So the number of valence electrons equals the group number. And we don't really deal much at all with bonding and transition metals, so you don't have to worry about those guys in terms of valence electrons, but really those sort of other groups you do. One exception would be group 8, which is our noble gases and helium. That's a really bad HE, I suppose. Helium there. Helium is group 8, but it actually only has 2 valence electrons, and that is because helium only has a total of 2 electrons, so it can't have more than 8. Obviously, can't have more than 2. So helium has 2 valence electrons. All the other noble gases have 8. 8 and 2 is kind of an important number in bonding. It is pretty much the basis of all bonding, which is what we'll talk about here in this chapter. The basis of all bonding is for everybody to basically achieve the same electron configuration as the noble gases. And that's because noble gases, right, as we talked about, are very stable. They're chemically inert. They don't react with other things. So the goal is for everybody to become like the noble gases in terms of their electrons. It's important to remember, though, that they don't become those elements because the number of protons remain the same, but they do become just like them in terms of the electrons that they have, which makes for a very stable bonding to occur. And that's the goal of both types of bonding, both ionic bonding and also covalent bonding, is to basically achieve just like our noble gases there. Also, while as we'll see, hydrogen, if we look at periodic table where hydrogen is, the noble gas that comes after hydrogen is helium. And helium is number 2, which means one major thing that you should always pay attention of is hydrogen only actually needs 2 electrons, and that's really important. It just needs to get over there to helium's configuration. So hydrogen should never, ever, I'll say it one more time, ever, maybe one more time for good measure, ever have more than 2 electrons to it. People always want to put tons of electrons and bonds and crap around it. So don't do that. Yeah, it just needs 2 electrons total, no more than 2. Pretty much everybody else is going to shoot for 8 to be really happy. Any questions on that there? Now, a Lewis dot symbol is pretty much the symbol. And once again, we use a dot to represent each of the valence electrons. And there's really kind of no rule per se for how you draw your Lewis dot symbols, other than really no more than 2 per side. And obviously, if there's 4 sides, 2 times 4 is 8. So again, 8 is the goal pretty much of everybody in terms of bonding to get there. A lot of times people will do like 1 at a time and come back and pair them up. But again, you can really do it however you want. Just don't put more than 2 per side is usually the rule. We only show valence electrons, which are the electrons that are involved in bonding. Again, you should also keep in mind that they still have those core electrons. They're, again, just not involved in bonding, but they are there at a lower energy level. And it's just these valence electrons that are shown in our Lewis dot symbols. So here's something I made when I was bored. I should get a hobby, but you know, I made it. Why not? So here's some Lewis dot symbols for all the elements, and we can see everybody in group 1 has 1, 2, obviously 3, 4, 5, 6, 7, and 8. Once again, our helium only has 2, as again, as I mentioned, that is pretty much where hydrogen needs to get to. Now, because we kind of skipped around there, chapter 11, and they moved it to the end of the semester, we're going to talk a little bit about some periodic trends, why we have a periodic table sitting up here, because it's really helpful in terms of bonding and sort of what's happening with bonding and why we see certain things bond in certain ways. That's not what I want. Try that again. There we go. All right, let's try that there. There we go. All right, so a couple of things about some periodic trends. One important periodic trend is what is known as ionization energy. And ionization energy is the energy required to remove an electron from the gas phase. And when we talk about the periodic table and ionization energy, it increases as you go this way, and it decreases as you go down. So again, if you have a really high ionization energy, it takes a lot of effort to remove an electron. If you have low ionization energy, it doesn't take a lot of convincing for electrons basically to leave. Another important sort of trend is electron affinity. Electron affinity is the energy change that occurs when an atom gains an electron. So ionization energy is the energy required to remove an electron, and that's usually associated with cations being formed. Those are the positively charged ions as they lost electrons. Electron affinity is the energy change when somebody gains an electron. That's usually a result of what happens is an anion being formed as it gains electrons. The trend's not perfect, but the general trend is electron affinity increases as you go up and to the right, decreases as you go down to the left. Another sort of trend that's important, and we'll talk a lot about it in this chapter, is electronegativity, which is different than electron affinity. Electronegativity is the ability of an atom to bring electrons towards itself. And electronegativity increases as you go this way on the periodic table. And it decreases as you go down. The most electronegative element you could have is fluorine. Is the most electronegative element you could have. That is because fluorine pretty much is as far up and to the right as you could go without hitting the noble gases. So those are, again, the most electronegative. Last sort of trend that will help us through sort of our conversation in this chapter is atomic size. And in terms of atomic size decreases as we go this way, and it increases as we go to the left and down on the periodic table. So these periodic trends are really important in terms of how bonding sort of works and why in cases we may have electrons being transferred and why in certain cases we may have electrons being shared. So if we take together all these sort of trends as we go up and to the right on the periodic table, which is like in this region where we have nonmetals. When we go up and to the right towards nonmetals on the periodic table, we have elements that are our atoms that are really small, which means their outer electrons, even their valence electrons, are actually going to be much closer to the nucleus. That means that they're going to be held a lot tighter, which means they have very high ionization energy. It takes a lot of energy to remove electrons, doesn't usually happen. They also have high electron affinity, which means they like to gain electrons. And they have high electronegativity, which means in addition to gaining electrons, they want to bring as many electrons towards themselves as possible. So all those things is typically what we see with nonmetals. They pretty much want to hang on to their electrons. They want to bring electrons towards themselves. And they are typically the ones that like to gain electrons because of that. And that's why they typically will become, when they do become ions, they become anions, are negatively charged, because they like to gain those electrons. As you go to the left and down on the periodic table, you have atoms that are larger, which means their outer electrons are further away from the nucleus, not going to be held as tightly. And that's reflected in low ionization energy, which means you don't have to put a lot of energy in there to remove electrons. They have very low electron affinity, which means they're not looking to gain electrons. And they have low electronegativity, which means, again, they're not looking to bring electrons towards themselves. So all of those periodic trends mean that as you go left and down on the periodic table, you have metals that basically want to give away their electrons. They don't really want to hang on to electrons. They're not looking to gain electrons. They basically have all these properties that mean that metals typically like to lose electrons and become positively charged or cations when they do become ions. Any questions on any of those periodic trends? We'll talk again about them in chapter 11 when we get there, but it is related to obviously bonding as well. Any questions on any of that? Wow. So as I said before, we could use these Lewis dot symbols to help us understand bonding. And once again, ionic bonding is always between a metal and a non-metal. And pretty much if you see that combination of a metal and a non-metal together, you could call it an ionic bond. You don't have to worry about it. You're going to be right. And what's going to happen in this case is based on those trends that we just talked about, the metal, which really doesn't want to hang on to its electrons, is going to transfer its electrons or some electrons to the non-metal, which goes, cool, I like to pick up electrons, I'll take them. And the result of that is, again, we're going to get ions that are formed. We're going to get a cation, which is a positively charged ion from the metal, and an anion, which is a negatively charged one from the non-metal. And again, it is the electrostatic attraction that holds that together. That is basically opposites attract. Once again, no sharing of electrons in an ionic bond. Now, covalent compounds have covalent bonds, and they are between two nonmetals. So once again, if we look at our little table here, pretty much our nonmetals are all pretty much in the same location on the periodic table, which means that they have very similar trends like electronegativity, ionization energy, and atomic size. And as we were just talking about, nonmetals typically do not want to get rid of their electrons. They want to actually gain electrons. So what happens when you get two nonmetals together is they both pretty much want to hold on to their electrons and take somebody else's electrons. So the best that they could do is pretty much agree upon, we'll share. Is the best that they will do. There will not be a transfer of electrons like we have when we have metals and nonmetals together, because they have very different periodic trends. The two nonmetals will share. And as we'll talk about in this chapter, that sharing of electrons, again, may be equal or unequal. And we'll talk about how you determine sort of which one's which. So general rule says that any atoms with low ionization energy will typically form cations. Again, that means it doesn't take a lot of convincing in terms of energy to remove an electron. Things with high electron affinity means that they like electrons, right? That's sort of what affinity means. And again, they typically will gain electrons and form anions. Any questions on that there? So that tells us, as we were just talking about, based on sort of those trends, we do expect metals to lose those electrons. We expect nonmetals basically to gain them. And that's why in an ionic bond, that's what happens. We get that transfer of electrons because, again, the metals are pretty much take my electrons, and the nonmetals say, no problem, we'll take them. And then we get that transfer of electrons, as opposed, again, in that covalent bond where they just want to share because they both really want the electrons. So let's take a look at an example here. This is lithium fluoride. Lithium is a metal. Fluoride is fluorine, which is a nonmetal. So as soon as I see basically that combination together, metal and nonmetal, I know this is going to be an ionic bond that's going to happen, and I don't have to think twice about it. I also know that it's going to be the metal, because of those trends, that's going to transfer the electron over to the nonmetal. So that's exactly what's going to sort of happen here. So if we take a look at lithium, lithium is group number 1, which means it has one valence electron. And I'm going to write the electron configuration so we can kind of see what's happening with that, which I think is important. And again, if we look at this number as 1, this is the second energy level. That is the one valence electron that we see in the picture. So that would be the valence electron. These two are what are referred to as the core electrons, not involved in bonding, so they're not pictured. So the one electron that we see there is that guy there. Our fluorine here is group 7, which has 7 valence electrons in this case. And if we write the electron configuration, 1s2, 2s2, 2p5, and again, this bunch of electrons right here are on the second energy level, which is the highest. That is 2, and that is 5, which is the 7 valence electrons that we see in the picture. So once we get these two guys together, our metal and our non-metal together, we're going to get a transfer of our lithium's electron over to our fluorine. The result of that is we will then end up with a lithium that has lost an electron and becomes positively charged at that point, right? It has one less electron. The fluorine's okay because it has room here. P orbitals, by the way, subshell, can hold a maximum of 6 electrons. It only has 5, so it's actually going to put that electron right in there, and it's going to pick up that electron. And when it picks up that electron, it will also then become negatively charged in this case. And we do typically, when we draw Lewis structures for ionic compounds, include the charges in the pictures on the right-hand side there. That indicates that there is no sharing of electrons, that there's been a transfer of electrons from the metal to the non-metal. Sometimes we put brackets around at least one of them or something like that. Now, if we look to see what happened here as a result of gaining and losing electrons, it is lithium that gave away this electron, which means what it is left with is 2 electrons, which is 1s2. And on the periodic table, number 2 is our friend helium. Yeah. And by giving away that 1 electron, what lithium is able to do is now basically have the same electron configuration as helium, which is a noble gas, and it makes it really happy in that situation. The fluorine picks up the electron at the end there and becomes 1s2, 2s2, 2p6. That is 6, 8, 10 electrons. On the periodic table, number 10 is neon. Yeah, number 10 is neon, which is also a noble gas. So fluorine, by picking up that electron from lithium, is able to achieve noble gas configuration. Question? It would not. So it picked up the electron from lithium. So with a -1 charge, it has 1 extra electron. It did start at 2p5 with its 9 electrons, but now by picking up the electron that was transferred from lithium, and now has 10 electrons, which goes forward on the periodic table if you look to the noble gas that comes after it. Both of these elements, by losing and gaining electrons, have achieved noble gas configuration. And that's really the purpose of all bonding, is for everybody to end up just like the noble gas. Once again, these elements are not helium and neon because they still have the right number of protons to be lithium and fluorine, right? They just have the same electron configuration. Yeah. No, so they actually have the same electron configuration, and that is what is being referred to as being isoelectronic. So lithium with a +1 charge and helium have the same electron configuration. And that, again, is the purpose of bonding, is for them, again, not to become those elements, but have the same sort of electron arrangement as those elements. Because as we know, noble gases are chemically inert. They're pretty much stable. And that's the goal of what everybody wants to sort of become like. They want to become like those noble gases in that case. And that's what is referred to as being isoelectronic. Same thing here, fluoride, which has a -1 charge, and neon is the same electron configuration and isoelectronic with each other. When you see these brackets, for example, around helium or even around neon, that means the electron configuration for the noble gas. So it represents, 1s2 basically for helium is electron configuration in that case. Other questions? So in an ionic bond, how they're able to achieve that stable noble gas configuration is metals will give away electrons and they move backwards on the periodic table to the noble gas that comes right before them. Nonmetals will pick up those electrons and go forward on the periodic table to the noble gas that comes right after them, hitting both of them in a very stable arrangement and making a very stable ionic bond. Any questions on that there? There's absolutely no sharing of electrons here. Once again, that unit there is held together by the opposites attract there. That positive charge of the lithium ion together with the negative charge of the fluoride ion, and that's what makes an ionic bond. It's a very strong bond. That positive negative attraction is kind of one of the strongest things you could have, is that positive negative sort of electrostatic attraction. And it does increase with sort of the number of the charge. So something that's +1 and -1 will be held weaker than, say, a +3, -3 sort of attraction. There'll be a much tighter and stronger sort of bond. This is always the type of bond that occurs whenever you have a metal and a non-metal hooking together. And the reason, again, for that is those trends. Metals have all the trends to say, I'm going to get rid of my electrons. And non-metals have all the trends to say, cool, I'll pick up the electrons. So we get that complete transfer of electrons from the metal to the non-metal. Let's take a look at another example here. Calcium is a metal. Oxide is a non-metal. So once again, we have the combination that we need to know that this is an ionic bond. And we know from that we will get that transfer of electrons that's going to happen from, in this case, our calcium to our oxygen. We look at calcium as group number 2 on the periodic table, which means it has 2 valence electrons. And if I write out the electron configuration for it, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Could also be abbreviated if we take just that part of its configuration. That is 6, 2, and 10, and 18 electrons. And that is argon's configuration. And 4s2. That's sort of, again, shorthand for electron configuration. Basically, the bracket in argon represents its electron configuration. Then we continue on with calcium's to 4s2. If we take oxygen, which is group number 6, we'll have 6 valence electrons there. And it has an electron configuration 1s2, 2s2, 2p4 in this case. So what's going to happen in this case is our calcium wants to get rid of its electron. So it's going to send over an electron over to oxygen. Now, if calcium just laid up 1 electron, will it get itself to the noble gas? We look on the periodic table. If it loses just 1 electron, it ends up at. Yes, question? How do I know? How would I know it has 6? It's group number 6. So the number of valence electrons equals the group number. So oxygen is group 6 on the periodic table. Yeah. So we'll have 6 valence electrons. Yep. So valence electrons will equal the group number, and that's how we know calcium, which is group number 2, has 2. You could write the electron configuration, but much faster just to look at the periodic table, and it's be equal to the group number. Other questions? Yeah.
How do you know that calcium is 3p6?
It is. How do I know it is goes to 3p6?
Yeah.
Because it has 20 total electrons, and that would be the electron configuration. It goes to 3p6, and then 4s2 is actually where it ends. So it goes past 3p6. Up to 3p6, which is in the box, is argon's configuration. So up to there, that's 18 electrons if you count the top, and argon's number 18 on the periodic table. So that is why there's argon's in the little box there, the brackets. That means the electron configuration for argon, and then continuing on to 4s2 takes you more spots on the periodic table to calcium. And then that's what calcium's electron configuration. So it actually ends on 4s2 in that case. Yeah. We will. It's chapter 11 when we actually talk about that. For many years, we did chapter 11 before 12, which kind of makes sense. But they decided this semester to bounce it around to exam 4, I think, is where we get to chapter 11. So we'll get to chapter 11 and we'll learn all about writing electron. For now, you don't. I'm just putting it here because it helps you understand sort of why the bonding sort of happens and stuff like that. So And again, in a homework problem, you may come across some of it because they assume maybe that you did chapter 11 before you did chapter 12, you know, when they wrote those online homework, just so you know. So if anything with electron configuration should be in chapter 11 if you ever need to reference it for like homework. But it is relatable here to obviously what we're talking about here with bonding and what's happening. Other questions? Okay, so the original question is, if calcium only laid up one electron to oxygen, if we look on the periodic table, it's going to bounce back only to potassium, which is not a noble gas. So calcium wants to lose not one, but both of its valence electrons in this case. And that's okay because when we look at oxygen, that p subshell there could actually hold a total of 6 electrons. So it's not a problem for oxygen. It's got place for both of those electrons basically to end up with. And when calcium is able to lose both of those electrons, it will end up as calcium with a +2 charge. And now at this point, once it makes the +2 charge, it has lost these 2 electrons here, which are the same 2 electrons here. And now it will actually only have 18 electrons, just like argon on the periodic table. And it will achieve argon's electron configuration. So here it was able to move 2 places backwards on the periodic table by getting rid of both of its valence electrons to achieve argon's configuration. The oxygen is okay because it can pick up both of those electrons, which means argon will now end up with a -2 charge because it picked up both of those electrons. And as I said, it has room actually for both of those right there. And if we write the electron configuration for oxide, which is oxygen with a -2 charge, 1s2, 2s2, 2p6 now with those 2 extra electrons that have come over. And if we count up the numbers on top there, that is 6, 2, and 2, which is 10 electrons. And on the periodic table, number 10 is neon's configuration, yeah? So oxygen moves forward 2 places by picking up 2 electrons and ends up at the same electron configuration as neon. So now both in this case, calcium and oxygen have achieved that noble gas configuration, and they're very stable in this ionic bond. Once again, there's no sharing of electrons here. It is that +2 attraction to the -2 charge that holds that kind of unit together. Any questions on that? So what happens if we take a combination of these 2 examples and put those guys together? So let's say we took our friend calcium here, which has its 2 valence electrons. And once again, that is the 2 valence electrons that we see in the picture. And we take a fluorine that we used in the first example, which had 7 valence electrons. And again, that is the 7 valence electrons that we see here in fluorine. Now what's going to happen is our calcium is going to send over an electron. At this point, can that fluorine take any more electrons? It cannot, right? It can only have a maximum of 8, which means it's kind of full at that point. And if we look at its electron configuration, it pretty much just got 1 spot left for an electron to go. So in this case, that's not going to make calcium happy, as we were just talking about, because that's only going to drop calcium back to potassium, which doesn't have the same ring as a noble gas configuration as alkali metal configuration. Doesn't sound good. So in this case, we need not 1 fluorine, but we would actually need a 2nd fluorine. And that 2nd fluorine now would have a spot for that 2nd electron for calcium to give away. The result of this is we will end up with a calcium that was able to lose both of its electrons, 1 to each of the fluorines. And now we'll end up with 18 electrons and end up with argon's configuration. I'll spit that out maybe. And we end up with a fluorine here that has picked up 1 electron and becomes negatively 1 charged. And we pick up a 2nd fluorine that has picked up 1 electron and becomes negatively 1 charge. Questions? Say again. Each calcium would be bonded to 2 fluorines, yeah, in this case. And the result of this is each of the fluorines picked up 1 electron, which means Each of these fluorines have a 1s2, 2s2, 2p6, or 10 electrons. Are they both achieve neon's electron configuration? So in this case, all three of these elements have been able to achieve noble gas configuration. The calcium by giving away an electron to each of the fluorines picking up just one electron, and now everybody's happy. I think we talked about it at the end of like chapter 4, maybe, when we take a cation and an anion, right? And we put it together to write the formula. So when we take something like calcium that has a positive charge and we put it together with fluoride that has a -1 charge, when we put a positive and negative together, the charge should equal what? Charge should equal 0, right? So if you remember, that is why we need not one of these, but two of these. And the proper formula for calcium fluoride is 1 calcium and 2 fluorides. The reason we tell everybody to put a positive charge and negative charge together in the simplest way to equal 0 is it's really the bonding. It allows everybody to reach noble gas configuration. If you don't balance out the positive charge and negative charge when you put it together in the simplest fashion, somebody in that group did not reach noble gas configuration, is not happy, is not a stable bond. It won't make an ionic bond. So the real reason why we say positive and negative put together in the formula to equal 0 is actually the bonding part of it, so that everybody's able to achieve noble gas configuration. Any questions on that there? Not necessarily that one, but you are trying to achieve basically 8 electrons to be like the noble gases. So you could achieve argon's configuration like calcium did, right? So it doesn't necessarily always has to be neon or argon, but the goal is to get everybody to basically group 8 in terms of their electrons. And hydrogen only needs to get to group 8 to helium, so it should only have 2 in that case. But everybody else wants to get that 8, which 8 is a really important number, as we'll talk about obviously in bonding. With covalent bonding is what's referred to as the octet rule. And that's what everybody's trying to achieve, basically, to get to 8 valence electrons. Other questions on that? Questions on ionic bonding here. So we can use Lewis dot symbols here to show ionic bonding. When you are drawing these symbols for ionic bonding, it's really important to make sure that you do include the charges, because again, it implies that there's no electrons being shared here, and that electrons have been fully transferred from the metal to the non-metal. Any questions on that? All right, then let's talk about the other type of bonding, which is covalent bonding, and that's what we just went over. So covalent bonding is a little bit different than what we were just talking about, which is ionic bonding. The first major difference is what's involved, and what's involved is 2 nonmetals. And once again, as we talked about earlier, because of their position on the periodic table, when 2 nonmetals get together, they pretty much both want to hang on to their electrons and grab up electrons. So this is the situation where the best we're going to do is sharing of electrons is going to happen when we have 2 nonmetals together. And again, as we'll talk about a little bit later here, it could be unequal or equal sharing of electrons. But the important part is there's some aspect of sharing that's happening. So Gilbert Lewis, hence the Lewis structure sort of name, anticipate bonding in a covalent situation as really the sharing of electrons. So in an ionic bond, it is the transfer of electrons that allows everybody to get to the noble gas configuration. In covalent bonding is that sharing of electrons that allows everybody to get to that noble gas configuration. So if we took a hydrogen atom and put it together with another hydrogen atom, they clearly would share all the same periodic trends since they're the same element. And what's going to happen is these electrons here will actually be shared between the two. You could represent it as dots. You could also represent it with a line. One line represents 2 dots or 2 electrons or a pair of electrons, and that's a single bond. 2 lines represent 4 total electrons or 2 pairs of electrons is a double bond. 3 lines represents a triple bond or 6 electrons, 3 pairs of electrons. And as we'll talk about, in some cases, it's necessary to double bond to get there, to get everybody happy in terms of the electrons. Sometimes it's required to triple bond, and sometimes it's just required to single bond to get everybody to where they need to be. And we'll talk about when to use them and when not to use them. So these electrons here that are being shared between the hydrogen atoms, these two count for the hydrogen on the left, and these two count for the hydrogen on the right. That gives hydrogen 2 electrons in each of these cases. And as we talked about before, that's all hydrogen needs to do is get over to helium, which is number 2. And that is what hydrogen should always look like. So when you are dry on hydrogen, once again, should pretty much just look like that. Should always be on the outside. Otherwise, it will have too many bonds. You should never find yourself like triple bonding hydrogen and putting dots. That is definitely wrong. So it should always basically look like that when you're drawing hydrogen. This is what is referred to as a covalent bond. It is the sharing of those electrons. Those electrons which are negatively charged are attracted to the nucleus of one hydrogen in this example, and also attracted to the nucleus of the other hydrogen. So the nucleus is positively charged. So that kind of mutual attraction between the two atoms within the bond is what sort of locks those electrons in place between them and kind of keeps them obviously bonded together. Any questions on that there? Now you can show the bond however you like. Personally, most of the time, people will show the electrons involved in a bond as a line, but you can just as well show them as dots if you like. So it is your call on how you want to do it. I personally will always show sort of those electrons involved in a bond as a line, but you can use the dots if you would rather use dots. So let's take a look at another example here. We have fluorine, which is group number 7, which means it has 7 valence electrons. And again, here it's going to share these electrons, as obviously they are both fluorine in this case. And as we can see on the bottom there, you can represent this with all dots if you like. Or again, for those electrons involved in the bond, you could show it as a line. And in this case, by sharing electrons between the two fluorines, the fluorine on the left ends up with 8 electrons, and the fluorine on the right, by sharing those guys in the middle, end up with 8 electrons, which once again allows them to get to the noble gas sort of configuration and make a stable bond. So just like in ionic bonding, the same sort of goal is here in covalent bonding. The only difference is how it's achieved. In covalent bonding, to get to 8, it's achieved through sharing electrons, and an ionic bond is achieved through transferring electrons from a metal to a nonmetal. Any questions on that there? Now, also really important when you draw Lewis structures like this for covalent bonding, a couple of things. In most cases, there's not a charge unless it happens to be an ion that you're drawing. But in most cases, it's going to be sharing electrons and you won't see a charge. But there's also 2 different types of electrons that we see in these pictures. And let's talk about the differences between them. All the ones pictured here that are dots, they are not involved in any type of bonding. And you know this because there's no element written on the other side of it. And these are what are referred to as non-bonding electrons, or if you're old like me, lone pairs. I probably will call them lone pairs most of the time. Nowadays, books call them non-bonding electrons most of the time, but non-bonding electrons and lone pairs are basically the same thing. So both names are used. Now, the electrons in the middle here, which are involved in bonding, has a very creative name. Those are what are referred to as bonding electrons. So when you draw your Lewis structures, you should always show all the electrons, both the non-bonding electrons, which should always be shown as dots, and the bonding electrons, which in most cases people will show it as lines. But again, you can use dots if you want for your bonding electrons. Any questions on that there? This is also really important when we start talking about geometry and identifying how many bonds there are and lone pairs there are. It's really helpful to make sure you have all that on your picture, obviously. So a Lewis structure is a representation, again, using our Lewis dot symbols. Once again, as I mentioned earlier, only the valence electrons are shown, but obviously all these elements still have those core electrons, which are not involved in bonding. It's just those highest energy electrons that are involved in bonding. So we take a look at water, which is another example here of a covalent bonding happening. And in this case, water, the oxygen is able to achieve 8 electrons by sharing with both of the electrons. And also each of the hydrogens is able to achieve 2 electrons by sharing with the oxygen that is there. Once again, that's going to make everybody happy. Everybody hits where they need to hit in terms of electrons and creates a very stable sort of bond. The purpose of all bonding, purpose of all sort of chemical reactions, and in a lot of cases, is to minimize sort of energy and create something that is more stable because of it. And that's really the goal of bonding as well, is to sort of minimize everything to a much stable level in terms of how these atoms are interacting with one another. So as we've been talking about it, but officially here, that is the main rule of bonding, which is the octet rule. And basically the octet rule means 8, and everybody will continue to make bonds until basically they have 8 valence electrons around them. Once again, our only sort of exception there is going to be hydrogen. That should only have 2 and no more than 2. And again, as I mentioned before, because of that, you should never ever put hydrogen in the middle of a compound. Should always be on the end, which is basically one bond to it, is how it will end up so it could get to helium. Now, we want to always make sure everybody meets the octet rule, especially with covalent bonding. And sometimes people sort of want to do that by double bonding or triple bonding, like I said, sort of right out of the box. And again, usually single bonding is sort of the way to go. And as we'll talk about, kind of save double bonding and triple bonding action to try to fix any type of problem where somebody doesn't get to a octet rule. So it's very common. People just want to keep drawing lines and bonds and stuff like that. So it's really important to, as we'll talk about in this chapter, sort of follow the rules of how to draw these things. All right, so a single bond, once again, can be represented by a single line, which represents a pair of electrons or a grand total of 2. And again, in the case of fluorine, that's all it needs. It just needs a single bond. It doesn't need a double bond or triple bond or anything like that to achieve that. Now, if you get to something like carbon dioxide, it actually does need to double bond, not once, but actually needs to double bond twice in that case. We do it with all dots being shown here. The carbon, by double bonding on both sides, able to achieve 8 electrons. Each of the oxygens are also able to achieve 8 electrons. And once again here, sometimes it does take a double bond to sort of fix a situation where somebody has not met the octet rule. This is also a good example, and we'll talk about that. You actually usually want to kind of, bless you, go in that order of, I want to single bond everybody. Then if somebody doesn't meet the octet rule, I want to double bond. If that doesn't fix it, if there's a chance to double bond again, you would want to double bond again before you go to a triple bond. So you kind of want to go in that order, single to double to triple. And that usually will give you a fairly good picture when you're drawing these, especially for covalent bonding. And again, sometimes a triple bond is necessary to achieve that electron configuration of 8. In the case of nitrogen, by sharing those 6 electrons in the triple bond, each nitrogen is able to achieve 8 electrons. And here in the carbon, where it's triple bonded, by sharing those 6 electrons and also sharing 2 electrons with the hydrogen, allows the carbon to get to 8. And also, once again, as you can see here, allows our hydrogen just to get to 2 electrons. So As I said, sometimes it does require to get to a triple bond to achieve that octet rule and make sure that everybody's sort of stable and happy in that case. So we're talking about obviously sharing electrons here in covalent bonding, and it really is that one property here that's really the big factor in the sense of how these electrons are going to be shared. So as we just talked about, electronegativity is that ability of an atom to bring electrons towards itself. And once again, it is increasing this way and decreasing, with fluorine being the most electronegative element you can have. Now, again, as I said, fluorine is as far up and to the right as you can go. The only thing further to the right are noble gases. And frankly, noble gases aren't interested in bonding. They are chemically inert. So that is, again, why everybody's trying to achieve that electron configuration and be like them. So really, noble gases are considered a lot of times to have like no electronegativity. They're not really interested in sort of bonding and stuff like that. Question? Or, yeah. Yeah. Where you have La and AC and all that kind of guys? No, they're not. Are you asking, are they noble gases? Is that what you're asking, or no? Yeah, but they remember that they actually do fall like where they should go in the periodic table is technically right here. So these two rows would actually be here further to the left. And they are metals. They're sometimes referred to as, we think we talked about, intertransition metals. So they would fall more in terms of electronegativity, like what you would see with, kind of transition metals in that area. No. What's that? It would actually be right there. They go right, yeah, right there below Y, basically, is where LA should be, and AC is actually right below that. And then the rest of it, really the two rows there on the bottom actually start with CE and TH. The other ones actually are kind of up in that spot where they go. So I think they just kind of printed it that way. So and that's why it says LA through LU on that one box. And that's to tell you that basically the bottom row should go right there on the periodic table and stuff like that. Other questions? Okay, so let's talk a little bit about electronegativity and so how it affects our bonding. So when we have a bond like our hydrogen, because both of them obviously is hydrogen, they have the identical electronegativity and all the other properties are going to be identical. So what happens when these electrons get shared between them is we would expect the electrons to be shared equally between them. They're going to have a sort of an equal pull towards each of them. And what that's going to result in is, if this sort of smears, the electrons will have sort of an equal distribution of electrons between those two, kind of like a rope. If you kind of both people pull equally, rope's really not going to go anywhere, right? So we got kind of an equal distribution of everything going on there. And the result of that is a certain type of bond where we would expect the electrons to be shared equally. So we would expect this to be shared equally, the electrons. This is what is referred to as a nonpolar covalent bond. Or most people leave the covalent part out and just call it a nonpolar bond. So a nonpolar bond, and I guess most people will call it, is implied to be covalent because it is sharing of electrons and it's two nonmetals that are happening here. And you result in equal sharing of electrons. The result of this is, because there's an equal distribution basically of electrons throughout that bond, there is no side of that bond that has a charge. So it's kind of like neutral, if you want to think about it. It's kind of a neutral sort of bond. Electrons are nicely evenly sort of distributed with all the positive charge that there is in the nucleus. And overall, there's no positive or negative side to that bond. And that is a nonpolar covalent bond when you have equal sharing of electrons. Now, what happens if we swap out a hydrogen, say for a fluorine, and we take something like this? Now we no longer have the same two nonmetals involved, and we do have some differences in electronegativity values here. We know from our conversation, fluorine is the most electronegative atom that there is. That means when fluorine and hydrogen get together, they're still both nonmetals, so they're both going to share the electrons. But because fluorine is more electronegative than hydrogen, we would expect the electrons to actually be, the smear is my electrons, hanging out a lot more towards the fluorine side than the hydrogen side because of that. The end result of that is we get a different bond that forms than what we just saw. We would get a bond where if the electrons are hanging out closer to the fluorine side, will the fluorine side be more positive or more negative in this case? Should be more negative, right? Because the electrons are hanging out there. So the result of that is we get what is referred to as a partially negative charge, and that's a delta negative, and a partially positive charge that happens here. Do you have a question? It's because of those periodic trends. Basically, as you go up and to the right is the smallest atom, yeah, which means all its electrons are closest to the nucleus than anybody else, pretty much. And that means that the outer electrons are going to be held a lot tighter, and they're not going to want to go away, their electrons. And because of that really positive charge there, it's going to be able to grab electrons a lot more than other people, or bring electrons towards itself because it's not so big, right? If you have something that's really big, that positive charge is kind of hidden by all the electrons, right? So the full brunt of that positive charge isn't felt by those electrons that it wants to grab. So when you have something that's smaller, you're going to feel that positive charge a lot more, and it's going to be able to grab those electrons a lot easier, or bring them towards each other a lot easier. Yeah. Other questions? Now, we can also represent this by an arrow, which is very commonly used in bonding. And this is what is sometimes referred to as a bond dipole arrow. And it always points to the more negative side of the bond. And the part in the back that makes like a plus always goes to the more positive side. So we always shoot this arrow. And that is what is sometimes referred to as a bond dipole arrow. And it indicates basically the separation of charge within that bond. And in this case, obviously the fluorine being more electronegative should be more negative. So it always points to the more negative, back end always to the more positive side of the bond. Why is it just a partially positive charge and partially negative charge, and not a full positive charge and full negative charge? They are. So there is still some aspect of sharing that's happening here. And so we think about our sort of tug of war rope there. We got fluorine pulling really hard, right? But the hydrogen is still hanging on for the ride, right? As he gets dragged around, but he's still hanging on. And that's what's happening here. Hydrogen is still able to hang on to its electrons. So there is still sharing that's going on. So we don't get the full transfer of that electron like we get in an ionic bond. In an ionic bond, nobody's hanging on to them. They're just completely being transferring. So we get the full positive charge for the cation and negative charge for the anion. It is. So in a polar bond, which is what this represents, by the way, this represents a polar covalent bond. Or again, people just call it a polar bond. A polar bond is the only bond that will have that arrow sort of drawn. So we do not draw for a non-polar bond because there is no separation of charge. But to answer your question, it always points to the one that is more electronegative, which basically means it's the more negative side of the bond. Yeah. Other questions? So in a polar covalent bond, we have unequal sharing of electrons happening. And that sort of unequal sharing of electrons is really driven by the difference in the electronegativity between the two elements that are in that bond. Any questions on that there? Okay, so that's sort of what we just talked about there. So again, like I said, both polar bonds and non-polar bonds, they are both covalent. And again, a lot of times people will just call them that polar or non-polar. And again, sort of the covalent and sharing of electrons implied by that. But you could call it either way. I'll accept polar or non-polar versus polar covalent or non-polar covalent, as long as you understand, hopefully, that it is obviously a covalent bond. All right, so there's sort of what we talked about, represented by that arrow. Once again, always pointing to the more negative, and the part that kind of makes a plus to the more positive side of that bond. All right. So to sort of summarize the three different types of bonding we talked to up to this point, on one end of the extreme, we have an ionic bond. And an ionic bond always between a metal and non-metal. And again, because of their differences in those periodic trends, we're going to get a full transfer of electrons from the metal to the non-metal. Metal always becoming the cation, which is positively charged, full transfer of electrons, and the non-metal becoming our anion, which is negatively charged. And again, no sharing of electrons here, that electrostatic attraction that holds that together. So something like sodium chloride is a good example of that. And you could always, once again, recognize an ionic bond or know that it's ionic when you see the combination of those two things, a metal and non-metal. Ionic transfer of electron, ion should be involved. On the other end of the extreme, we have a nonpolar covalent bond, or just a nonpolar bond. That is always going to be between two nonmetals. And here we will have equal sharing of electrons. That results in really sort of a neutral bond, say like our F2 or H2 as an example. And sort of in the middle of those two things is a polar covalent bond. Which is also between two nonmetals. And here it is unequal sharing of electrons. And obviously our example here is like our HF, where we could draw again that arrow pointing to the more negative side. So one end of the stream, we got a complete transfer of electrons, metal to non-metal. Other end, we got nice, perfect, equal sharing of electrons, results in essentially a neutral type bond. And in the middle, we have unequal sharing of electrons, but not so unequal that they have transferred. And we have some aspect of sharing, and the result of that unequal sharing of electrons creates a separation of charge because the electrons are on one side versus the other, and creates that partially negative charge and partially positive charge. Yeah. Yeah, so when we talk about really bond here and bond polarity, which is sort of what we're talking about here, when we talk about bond polarity, it's really talking about between just two elements in a particular bond. And that two elements could be in a bigger molecule as a whole. But, you know, for example, water has two bonds, right? It has an oxygen hydrogen bond on one side and the same oxygen hydrogen bond on the other side. So when we talk about bond polarity, we're talking about just simply the bond between, say, one of the oxygens and one of the hydrogens. Is it going to be shared equally or unequally? When we talk about molecular polarity, and is that whole molecule polar or non-polar, there's other things we have to look at, which we'll talk about towards the end of the chapter. But there's two different sort of polarities that we talk about. And what we're talking about really now is sort of bond polarity, which is just simply between these two elements, how would we expect the electrons to be shared? There is a place where that would be the same as molecular polarity, and as you said, it actually would be with the diatomic molecules, because they only have one bond. Whatever that bond is, the molecule is going to be the same. So that's the only place where it's sort of bond polarity, and we'll talk about later on in the chapter, molecular polarity are basically going to be the same, and it's only because in diatomic they got one bond, so whatever that bond is pretty much what the molecule is going to be. But when you have something like water where there's multiple bonds happening, you have to look at a couple other things that we'll talk about later on. Other questions? Yeah. So as I said before, it is really the electronegativity that helps us determine, how those electrons are going to be shared. It could help us determine, do we think these electrons are going to be shared equally? Are they going to be shared unequally? Are they even going to be ionic? In reality, you really don't need electronegativity to figure out ionic, because as soon as you see metal, non-metal, you're good to go. But you can use it in a case to help you with that. So electronegativity is related to the electron affinity and ionization energy. So elements that have high electron affinity, they like to gain electrons. They typically will also have high ionization energy, which means it takes a lot of energy to lose electrons, and that doesn't usually happen. So they want to hang on to their electrons. They will have a high electronegativity. And elements with low ionization energy, which means it doesn't take a lot of energy to remove an electron, and low electron affinity, which means they really don't like to gain electrons, will have a low electronegativity. So fluorine has high electron affinity and high ionization energy and has a high electronegativity, while sodium is on the other end of the spectrum. They got basically low of both, low electron affinity and low ionization energy. That is why what we see with our ionic compound, we take a metal, which is basically left-hand side of the periodic table, and put it together with a non-metal, which is upper right. Very big differences in those properties. And again, our metal is willing to lose its electron pretty easily, and our non-metal is willing to accept the electrons really easily. So that's why, again, we get that transfer of electrons that happens in an ionic compound. In a covalent compound, because they're both basically in the same spot on the periodic table, they have very similar sort of properties. So they both want to hang on to their electrons, as we talked about. And that's why we end up with sharing happening in covalent bonding. So how can we determine this? We can use a scale that was devised by a guy named Pauling. He did a lot of work with a lot of things, including came up with one of the first DNA sort of ideas of what it was. It was wrong, but he came up with it. That was good. But he was also very big on megadosing vitamin C, Pauling. But what he also came up with was the idea of electronegativity values. And on Pauling's scale, it went from 0 to 4, 4 being the most electronegative, and 0, not so much, or the least electronegative. So if you take the difference in electronegativity values, which is sometimes referred to as delta En, delta meaning difference, En meaning electronegativity, and you basically just subtracted 2 electronegativity values for the elements that are involved in the bond. If you get a difference between 0 to 0.4, that's considered a nonpolar bond, which means we're going to have equal sharing of electrons. If you essentially get above 0.4, which I guess we'll go with 0.5, to below 2, that is some type of polar bond, which means we would expect the electrons to be shared unequally. And typically above 2, which is not the case in all cases, is an ionic bond, which is no sharing of electrons, but a transfer of electrons. I'll be honest with you, there's a number of combinations that you could do the difference in electronegativity and get less than 2 and to still be ionic. So once again, for ionic, I wouldn't even worry about electronegativity. I would just worry about that's a metal, non-metal, it's ionic. You'll be pretty safe, and pretty much every time you have to make that decision. I would use probably the difference in electronegativity more so for covalent bonding and the sharing of electrons. And those cutoffs are important because it kind of tells you where, polar and non-polar sort of begins. There's also sometimes you will see if you take a difference in electronegativity and you get 0, this is sometimes referred to as a pure covalent bond. And a pure covalent bond is really a nonpolar bond. It is kind of like perfect equal sharing of electrons. So this would be a case where you have perfect equal sharing of electrons. And sometimes books will refer to that as a pure covalent bond. And it's basically still a nonpolar bond. It just means that's like this perfect is equal sharing of electrons as you could get. Any questions on that? So this is a electronegativity table, which obviously the numbers would be provided for you if you needed it. So let's take a look at how we could use this. So we'll take our examples that we saw earlier. We have sodium chloride. we had HF, and we had, we'll do F2. All right, so if we're going to use this value, we can again see, here's our fluorine, which is upper right, biggest number 4. And if we go down to the left there, numbers get much smaller. And to answer your question, there's kind of our guys on the bottom there. You can kind of see where they were earlier, their values in terms of those guys. It goes from like 1.1 to 1.2 or 1.1 to 1.7 for the other bottom row and stuff like that. So we will look up sodium. Sodium is 0.9 and chlorine is 3. So to take the difference in electronegativity, we just subtract it, larger from smaller, gives us a 2.1. And again, anything from 0 to 0.4 is nonpolar. Anything from 0.5 to below 2 is polar. And anything above 2 is ionic. And this would be our change in electronegativity values. So here we could clearly see we're above 2, and we would expect this bond to be ionic, no sharing of electrons. Once again, you really don't need this because that again is a metal and a non-metal, so I already know it's ionic. I don't even really need the numbers or the values to determine that it's an ionic bond. So let's take a look at the other one. We have fluorine, F2. This has a value of 4 and 4. So difference in electronegativity would be 4 minus 4 is 0. Difference of 0 is going to be a nonpolar bond, right? That also could be considered a pure covalent bond, as the difference in electronegativity is 0. Perfect equal sharing of electrons. If we look at our HF, our hydrogen is 2.1, our fluorine is 4. Change in electronegativity, 4 minus 2.1 equals 1.9. 1.9 is like the cutoff almost for ionic. So this is definitely going to be a polar bond in this case. And if I were again to draw the arrow, it should point towards the more electronegative, which is the fluorine. Now there is different degrees of equal and unequal sharing, right? Now 1.9 is very unequal sharing, right? They're pretty much all the way over there to the fluorine, but again, the hydrogen is barely hanging on, right, to its electrons as it gets dragged around. So, you know, it hasn't reached that point where they jump over and transfer. It's still able to hang on to it. Yeah, so the 2 value, again, the 2 value for ionic is sort of subjective in a sense. There's a lot of examples where ionic bonds will actually give you less than 2. So it's a ballpark number for 2. But usually the other cutoffs are pretty tight. And that's why I said for ionic, you don't really have to worry too much about the values. You could just simply go metal, non-metal, ionic, you're good. Yeah. Other questions? Yeah. No more gases typically will have electronegativity values of 0 because they're not really interested in doing much, right? Because that's what everybody's trying to become. So if you needed to use a value for noble gases in this sort of calculation, usually it's 0 is sort of what you would use for it. So why don't you try a few here? Let's do nitrogen and oxygen bond. Let's do sulfur and oxygen. Let's do carbon and sulfur. Let's do potassium and chlorine. And let's do carbon and hydrogen. So use the difference in electronegativity values to determine is it polar, ionic, or nonpolar. See what you come up with here. Okay, let's take a look since we're getting to the end here to make sure. We'll look up our values here. So 3 for our nitrogen and 3.5 for our oxygen. So our difference in electronegativity going to be 3.5 minus 3 gives us 0.5. 0.5 is a polar bond in this case. If we are to draw the arrow, it should point to which elements? Point to oxygen, which is more electronegative in this case. Any questions on that one there? If we look at sulfur, which is where are we at there? 2.5. Oxygen, which is 3.5. Our difference in electronegativity would be 3.5 minus 2.5. Once again, just take the larger number minus the smaller. That gives us a 1, which once again would also drop us into our polar bond. And we would draw the arrow towards the oxygen in this case. If I do potassium, which is 0.8, and chlorine, which is 3, and if I do the difference in electronegativity, 3 minus 0.8 is 2.1. That is going to be above 2, which means it's ionic. And once again, we really didn't need that because we know hopefully it's a metal and a non-metal together, so it should be ionic. For carbon, it is 2.5, I think. Hydrogen is 2.1. So difference in electronegativity, 2.5 minus 2.1, which is 0.4. That's going to be non-polar. And that is where our cutoff is. And the cutoff really is for those elements. Organic molecules are typically carbons and hydrogens, and they're non-polar. So that's why the cutoff is. Is that perfect equal sharing of electrons in this case? It really is not, but it's not enough to be called unequal sharing of electrons. So again, there is sort of a little wiggle room in terms of equal sharing. Lastly, we have carbon, which is 2.5. We have sulfur, which is 2.5. That's going to give us a 0 when we take the difference. That means that is non-polar as well. And that is because they are opposites of each other in terms of a diagonal rule. Carbon is further up on the periodic table. Sulfur is further to the right. They cancel their differences. So you see that in a couple places like nitrogen as well. So chlorine, this sort of diagonal down and over one. And this is a good example of you definitely could have two different elements that can share electrons equally, just like you could have obviously the same elements share them